x of t is a Brownian motion. Another question to see that what you have understood. When we define, so look at the definition of Gaussian process that we defined and try to guess that it's a map from where to where actually. You see the definition actually. It's a map from where to where. I haven't talked about, when I defined Gaussian process, I didn't say that x of t's are maps from something to something. That's a key thing. In other words,
range is real.
They are real valued actually. That's what is the key thing. Okay. In other words, a real valued process, one-dimensional process, is a Gaussian process. If you take their increments, finite number of increments, and make a vector out of it, that vector is going to follow n-dimensional motion actually. Okay? So why I'm making this point? I'm making this point. Don't assume that a Gaussian process itself n-dimensional actually. So your previous definition was a definition about a one-dimensional Gaussian process actually. Okay? Maybe you can define it in higher dimensions, but you know, one-dimensional Gaussian process is Gaussian if you take the finite number of increments and they form a random vector actually, random Gaussian vector. Okay? So tabhi you can see actually that here you also have a one-dimensional Gaussian process that starts from 0, has a constant, you know, mu, has continuous path, and follows this process, you know, this identity, then it must be a Brownian motion actually. Okay? So why it should be a Brownian motion? Let's quickly go through the argument. Then we can finish here. All of these are going to be the things that are useful when we are doing our development theory afterwards. Okay? Proof. So I need to verify that this process X must satisfy what properties? The definition of the Brownian motion. So it starts from 0, we know it. It has a continuous path, we know it. The only thing that we need to do is this second and third property, that it follows the normal distribution. Okay? And it follows independence actually, independence of the increments. This is what is the key thing that we would like to show. So let's start with, for example, the third property of the increments. So let's think about, so for that I need to do what? I need to take some finite number of, you know, instants, and then consider the increment on, you know, each such instant, and I need to show that increments of the process on each such instant is, you know, can you visualize in your head what do you mean by increment for a random process? So I have a random process, okay, and I'm fixing two instants actually, so S and T, and I'm looking at its value, okay, its value at time S, and looking at its value at time T, and I'm talking about this difference. That's your X of T minus roughly X of T. And I'm saying that if you take any two other instants, for example these two instants, okay, and you know similarly see their values, the both values are going to be independent of each other. Alright. So I need to show what? That this x of t2 minus x of t1, already x of t1 minus x of t0 as well, after x of tn minus x of tn minus 1 are independent. ठीक है जी, they are independent. In order to show independence, so do I know about something about these increments? So I have an assumption that this process is Gaussian process. So if I make a vector out of, these
increments.
Increments. That must be the Gaussian vector actually. Follows the n-dimensional Brownian motion actually. Not Brownian motion, but normal distribution. ठीक है? So let's take, say, consider two abstract indices and consider two different indices. So I and j are two indices. And consider the expectation of x of ti minus 1 times x of, what do you say, tj minus x of tj minus 1, and I would like to compute this expectation. So if I compute this expectation, okay, and it turns out to be 0, does it going to prove that they are independent? And if yes, why? What at the moment we know about this process is that it's a Gaussian process, constant expectation, okay, and so these are the key things that you know about it actually. So if it is a Gaussian process, I know all these are. So you have a Gaussian random vector, okay. Now, if I can show that if you take any two vectors out of it, okay, and consider their product of their expectation, and that turns out to be 0, then it is going to show that any two pair is independent. Why? Because I already know that the expectation of x of ti minus expectation of x of ti minus 1 times expectation of x of tj minus expectation of tj minus 1 is 0. Why is 0? Because it's constant actually. So if you're going to compute this expectation, so this is mu and mu, so this becomes 0. So if this product also becomes 0, so equality would establish actually, and it's going to show that the increments are independent. Okay? This is what it's going to show. Alright, so how can I show it? I need to just simply take the product of it. We're going to take the product. So there will be 4 terms appearing at x of ti, x of tj minus x of ti, and x of tj minus 1 plus expectation of x of ti minus 1. Shall I write it directly? Okay. Let me just write it directly. So I'm saying what would be the expectation of x of ti times expectation of x of tj, provided that you know this as well. By the way, what would be the covariance of x of t, x of s times x of t?
Expectation of the product.
And
Can you see it?
minus mu square.
Minimum rate now.
Huh?
No.
We don't take a minimum.
Minus mu
We
square.
are
yes.
I less than j.
So if instead of x of s, if I take an increment here and take an increment here,
Mm.
what this would be? Okay. Let's think about the covariance of these two guys actually. Okay? Let me call it, this is AI, and let me call it, this is AJ, for example. So I'm talking about covariance of AI and AJ. So this is going to be the expectation
Yeah.
of AI, expectation of AJ, nahin, AI AJ minus expectation of AI times expectation of AJ. So this must be 0. ठीक है? तो हो जाएगा ना 0. So this must be 0. So this is the covariance of both. Now I'm asking the first term in this. Yeah. Okay. I'm thinking too much. Well, so what would be expectation of x of ti and x of tj? Keeping in view this. So the covariance of x of s and x of t is
Minimum of
s and t. So what's going to get?
minimum of T and INJ. T and
So you know the I
I
is smaller. So the first term is going to be.
TI.
Yeah, that's what I'm asking. That I would like to write directly that this is going to be Ti. So when you're going to compute the x of Ti and x of Tj minus 1,
Brownian.
I mean, okay, here's the thing. So I minus 1 is here, I is here, j is here, and j minus 1 is here. J minus 1 is here and j is here. Okay? You can say this is a misleading. Why? Because j minus 1 can be equal to I, which is fine.
can be left hand
You know, which is fine. So if you are taking the expectation of, say Ti and T minus J, then this is going to be, you can even assume this picture, for example, without loss of generality. Just assume this picture without loss of generality. Okay? But you will see that you will also get the same result if you keep J minus 1 here and I here. Actually, it doesn't make any difference. The result would be same. That's why I'm saying that when I is less than j, so I can be less than or equal to j minus 1. Okay? Either is going to be equal to j minus 1 or is going to be smaller than. Okay? So what I can write precisely for the second term is this. So imagine that I is less than j minus 1. This is going to be Ti. The third term is going to be Ti minus 1 Tj. So for sure Ti minus 1. And the fourth term is going to be,
Again TI minus 1.
so it's going to be Ti minus 1, and you can see that this is there. Okay? So this shows that the increments are independent. The final thing is going to be, we need to talk that, normally distributed kind of variable. Since this process is Gaussian, I don't need to worry about the distribution of this function. Why? Because it's for sure normally distributed. Why should we normally distribute to that?
when in the Gaussian, when n is equals to 1, it will be now.
Yes. So this is like n equal to 1 case. You just take one increment. So the Gaussian process take one increment or 10 or 20 or 100 increments. Okay. Their joint is always normally distributed actually. So if I just take one increment, so that would also be normally distributed actually. Simply no. So that's normally distributed because the process is Gaussian. So the only thing that you need to verify that it has mean, zero and variance with t minus s. So does it have mean zero? Indeed. Does it have variance x of t minus x of s? Okay. So what should be the variance of it? Can I say something sensible about it? This is going to be for sure expectation of x of t minus x of s square. Okay? And you do what you did here actually. You know, just split the square. So what would be the expectation of xt square?
It would be
So it's going to be t. So what would be the expectation of xs square? So it's going to be s minus what would be the expectation of x of t, x of s? So you may
2t.
assume without loss of generality that s is less than or equal to t.
then 2s
Okay? Then you have what you say 2s, so you get
t minus.
it's a Brownian motion. So here a Gaussian process which satisfies these properties is a Brownian motion. So see you tomorrow.